Okay, so sometimes integration by parts is not so straightforward. Sometimes it's hiding, and you got to seek it out, find it out. And that's what this video is going to show. It's going to show some weird things that can happen. So let's evaluate some more integrals. What about the integral of t cubed e to the t squared dt? So now right off the bat, again, I hope you think of u substitutions. This would be a good choice of u, but the problem with this is that if this is u, this is not our du, but it still might work. Wait, actually, it looks really good. Why don't we do it? I wasn't going to. You don't have to. There's another way of doing this problem. Let's do it. Think about u substitutions whenever you can. It can save some work. Because if we don't do a u substitution here, you have to be very careful with your u and your dv. Because we can't integrate this. I'm going to make a quick comment that if you wanted to do integration by parts, you would have to rewrite this as something that we could, or you could hold on, before I even say that. Since we can't integrate this, you might think that this is what we want to differentiate. But if we differentiate this and integrate this, we just get something even messier. We're going to get t to the 5th e to the t squared, which is even worse. Okay, so we want to integrate this somehow, and the only way to do that would be to write this integral as t squared times t e to the t squared, and then we could do integration by parts this way. We could integrate this, and that would become nicer. We could differentiate this, and that'd become nicer. So if you wanted to use integration by parts right off the bat, it's a little tricky. But I'm trying to always get you to think of other methods too. So let's do a u substitution here and see what happens. I think I know what's going to happen, but I want to show you what happens. Always be thinking of u substitutions if you can. So if u is usually the inside of some function, so the inside of an exponential is its exponent. If u is t squared, what is du? It's just 2t times dt, which we don't have yet, but we can get it. Right? This can be written as 2t times t squared times 1/2. Right? This is still the same thing because 1/2 times 2 cancels. T times t squared is t cubed. I haven't changed the integral at all, but I've written it in a nice way so that this is e to the u. This is du. Oh, and what's this? It's left over, but t squared is just u. So if we do a u substitution, it turns out we get something really nice. We get u, e to the u, du. So we'll still have to use integration by parts. But I think this integration by parts is much simpler and easier to find than this integration by parts. There's multiple ways of doing these problems. Try to do a u substitution if you think it's going to work out, or you can try to manipulate it into integration by parts. When you do integration by parts, try to find something that gets easier when you integrate, something that's easier when you differentiate. So again, our choice of u is probably bad here. Or, sorry, the choice of u is good. But our lettering, let's just call this a W. It'll make our lives a little easier. You don't have to. You could leave everything as U's. You can call it whatever you want. But if we rename all this with W's, now when we do our integration by parts, we can use U and V, which is a little bit more comfortable. So we're going to let U be W and dV be e to the W dW. So again, U is W, so du is just dW. And dV is e to the W dW. Its antiderivative is just e to the W plus a constant, but we don't need that constant because it will always cancel out. So it's 1/2 times the integral. Very, very important. It's 1/2 times the whole integral. And the whole integral by the integration by parts formula is 2 parts. You really need these parentheses here. We get uv, which is w e to the w, minus the integral of v du, e to the w dw. 1/2 w e to the w minus e to the w plus a constant. Again, technically the constant's in here, but a constant times a constant. It's all good. And then last but not least, what is w? W is t squared. We get 1/2 times t squared, e to the t squared, minus e to the t squared, plus c. I take this as your final answer. It's a little better if you factor out an e to the t squared. And actually, you could factor out again. You could factor a t squared, difference of squares, t minus 1, t plus 1. But I think this just makes it look nice enough. Check our answer by taking the derivative. You should get back what we started with, but I'm not going to do it for time purposes. The last video was too long. Let's do part B, integral of sine of ln of x dx. Now, what's wrong with what I'm about to show you? I want you to analyze what's wrong with this. Maybe pause the video. Think about it. U is easy to differentiate. That's great. dv is easy to anti-differentiate. That's great. So what's the problem? Everything looks happy. The problem is that this is not multiplication. For integration by parts to work, we need multiplication, but this is on the inside. We can't use integration by parts like that because they're not being multiplied. There's no multiplication happening here at all. Cannot let one of these be u, cannot let the other be dv. So we have 2 options. We could try some sort of u substitution, which I think would work. Or we could try a very creative new way of integration by parts. Watch this. You're going to like this. This is true, no? Is this not true? That's true, right? Now, we've got a product finally. We've got a product. And this is what's done all the time. If you can't integrate something, sometimes we just use integration by parts with 1. That's how you derive the formula for natural log. That's how one of the ways you can derive the formula for inverse sine is you just write it as the thing times 1 and use integration by parts. So I don't know how to integrate this, but I know how to differentiate it. And then this part, I know how to integrate that. I'd really like to differentiate the 1, but that'd go backwards. Okay. So this is what we're going to choose here. And this pops up with all sorts of things. If you only see one thing, no product, only just one thing, and you can't integrate it, this is a strategy. Multiply it by 1 and then use integration by parts. It looks a little silly, but we get some cool stuff. Check this out. It's very powerful. That's why I said this method's so powerful, because even if there's no product, it can work itself out. I actually don't know what this answer is going to be, but pretty sure this is what you do. Let u be sine of the natural log of x. So what's du? It's its derivative times dx. We'll have to use the chain rule. Derivative of the outside function, leave the inside function alone, and multiply by the derivative of the inside function. dv is just 1 dx. What's its antiderivative of 1? Just x. So integration by parts is going to say u times v, which is x times sine of natural log of x, minus the integral of v du, which is x times cosine of ln of x times 1 over x dx. We get some cancellation here. What have we got? X sine of ln of x. I love this example. Minus the integral of cosine of ln of x dx. And I'm sure you're saying right now, Jason, this sucks. This isn't any better. Right? This new integral is basically the same as the old integral. Jason, what's the deal? All right, let's scroll back. Our choice of u and dv. Most of the time, we want to think about number one. And notice I didn't say better. I didn't use the word better here. I said not worse. So question for you. Is this any worse? No, it's just as bad. I acknowledge it. It's just as bad, but it's not worse. I love this problem. I love this problem. This is one of my favorite problems in all of calculus. It surprised me too. I wasn't sure this was this kind of problem, but it is. I thought I would have to add this kind of problem. Oh, it's such a good problem. Okay, so we could just sit here and whine, or we could do integration by parts again. You might say, Jay, how the heck is that going to help us? Well, let's just do it. Have some faith. Have some faith. So just like before, again, this x sine of ln x is over here. We're subtracting some, integration by parts. Now we need to choose a u and a dv. Well, just like before, we can't integrate this, so let's let this be our u, or our w, if you will. I'm just going to call it u2. Why not? And then our du, or our dv, our dv2. I don't want to call it w and something else, but it's not the same u as before. Let's use integration by parts again. u2 is the cosine of ln of x. So du2 is negative sine of ln of x times 1 over x. Chain rule. dv2 was dx, so v was just x dx. We use integration by parts again. uv, oh, you don't want too many dx's. uv, which is x cosine of ln x, minus the integral of v to u. Again, the negatives are going to cancel here, so we're going to get plus. And the 1 over x cancels with the x. We're multiplying these two guys right here. We get x sine, oh, sorry, the x's cancel. We just get sine of natural log of x dx. Now, I hope at this point you're furious. You're jumping up and down. You're saying, Jason, this is exactly what we started with. I hope you're furious. What's going on? Jason, do you even know what you're talking about? Do we need a new calc professor? No, we don't. What we have is something beautiful. It doesn't look beautiful, but what have we shown? What have we shown? These are all connected with equal signs. All of these things are equal. So we know that this integral, we know that the integral of the sine of the natural log of x dx, this is what we've shown, is x times the sine of ln x, right? This, let's distribute that negative, minus x times the cosine of ln x, minus the sine of ln of x dx. This is what we've shown so far. And again, we don't know how to evaluate this. That was the problem that we started with. Don't think in one dimension. Think in 5 dimensions. Watch this. This stuff's going to blow your mind, unless you've seen it before. We have an equation here. Can I do this? Can I add this integral to both sides? Yeah, why not? You can add something to both sides of an equation. That's no problem. And boom. Just like that. What have we got? Now we have two of these integrals. We had one integral. We added another integral. Now we have two of these integrals. And what's our right-hand side? We're done. Almost. Isn't this crazy? We're almost done. We wanted to know what the integral was equal to. Well, we know what two of the integrals equal. Let's just divide both sides by 2. The integral of the sine of natural log of x dx. Let's also factor out. Let's divide both sides by 2 and factor out an x. It's the sine of ln x minus the cosine of ln x. We did it. Isn't that wacky? So sometimes when you use integration by parts, sometimes you don't get anything that looks any better. But as long as it doesn't look worse, you might have a situation like this. If you ever get back what you started with, it means one of two things. One, you may have just messed up and undone all your work. That happens. 2, it might be this situation. Okay. Again, an example of if you do mess up would be like a problem like this, where you started with this. And then when you get to here, if you choose the wrong W and dV in this second gold circle, you will actually get back to where you started with, and it'll be a disaster. It won't help you. If you choose the second one wrong in something like this, you could also get back to where you started, and then it'd be bad. But sometimes it's good. And if it's good, it'll look like this. So watch out for it. It can pop up. This shows two really kind of tricky techniques, but good techniques in the same problem. Integration by parts can be useful, even if there's only one thing that we can't integrate, but we know the derivative of. You can use integration by parts by writing it with a 1. And the second thing is sometimes you might just get what you started with, and then we add it to the other side, and we can solve by just dividing by 2. Check your answer. Use product rule and the chain rule on this thing. You'll get that it works out. Anyway, that's it for this video. That's all the real stuff of this section. Got 3 more videos just for extra stuff. Definite integrals. Well, definite integrals are just, I don't want to spoil it, but it's just review. And then we've got 2 selected homework problems videos for you. Anyway, good luck. Bye-bye. Have fun.